I know that you missed me, but my 2-week cold is finally over. I will catch up the videos for the topics that we've covered while I was ill, but today I'm going to talk about energy transfer in reactions. During reactions, energy is transferred between the reaction mixture and the surroundings. Some reactions give out heat while others take heat in. Chemicals store a certain amount of energy, and different chemicals store different amounts. If the product of a reaction store more energy than the original reactants, then they must have taken in the difference in energy between the products and the reactants from the surroundings during the reaction. But if they store less, then the excess energy was transferred to the surroundings during the reaction. The energy that is transferred between the reactants and the surroundings during a chemical reaction is usually transferred by heating. We did a number of experiments where we mixed various chemicals together and used a thermometer to work out whether energy was transferred to or from the reactants. If energy is transferred to the surroundings, the temperature of the surroundings will increase. If energy is transferred from the surroundings, the temperature of the surroundings will decrease. The overall amount of energy in the reactants and the surroundings doesn't change. This is because energy is conserved in reactions. It can't be created or destroyed, only moved around. This means the amount of energy in the universe always stays the same. An exothermic reaction is one which transfers energy to the surroundings. This is shown by a rise in temperature in the surroundings. The best example of an exothermic reaction is burning fuels, combustion. This gives out a lot of energy. It's very exothermic. Neutralization reactions between an acid and an alkali are also exothermic, as are many oxidation reactions. The reaction of potassium hydroxide with hydrochloric acid is a neutralization reaction. This reaction releases energy. It's exothermic. When sodium is added to water, it's oxidized, releases energy, and moves about on the surface of the water. The fact that energy is released shows that this is an exothermic reaction. Exothermic reactions have lots of everyday uses. Ones we looked at, some hand warmers use the exothermic oxidation of iron in air with a salt solution catalyst to release energy. Self-heating cans of hot chocolate and coffee also rely on exothermic reactions between chemicals in their bases. An endothermic reaction is one which takes in energy from the surroundings. This is shown by a fall in the temperature of the surroundings. Endothermic reactions are much less common than exothermic reactions, but the reaction between citric acid and sodium hydrogen carbonate is a good example, as are thermal decomposition reactions. We also learnt in B4 about photosynthesis being an endothermic reaction. Endothermic reactions also have everyday uses. A sports injury pack is a cold pack that can be placed on an injury, like a sprain or a strain, to reduce the swelling. Some sports injury packs use endothermic reactions. They take in heat and the pack becomes very cold. This is much more convenient than carrying ice around. Also, this type of cold pack is much more flexible than a block of ice, so it can be wrapped around an injury more easily. We carried out required practical number 10, energy transfer of reactions. The amount of energy transferred during a reaction is proportional to the temperature change of that reaction. So if you measure the temperature change of a reaction under different conditions, such as with different amounts of reactants, you can compare how much energy the transfer changes. You can find the temperature change of a reaction where at least one reactant is a liquid or solution by taking the temperature of the reactants, mixing everything together in a polystyrene cup, and measuring the temperature of the solution at the start and at the end of the reaction. The biggest problem with taking measurements like this is the amount of energy that's lost to the surroundings. Using a polystyrene cup helps to insulate the reaction mixture more than a glass beaker would, but some energy is still transferred by heating. You can reduce it a bit more by putting the polystyrene cup into a beaker of cotton wool to give more insulation, and putting a lid on the cup to reduce energy lost by evaporation. This method works for the reactions of solids with liquids, like a reaction between metals and acid, or metal carbonates and acid, as well as for reactions where you mix two solutions, like neutralization reactions between acids and alkalis. You can use this method to investigate what effect different variables have on the temperature change, and so the amount of energy transferred. For example, you could investigate the effect that changing the amount of reactant has on the energy transferred. This could be done by repeating the experiment with a different mass or concentration of one of the reactants each time. When we did this experiment in class, we used hydrochloric acid and sodium hydroxide solution. We started with 30 centimeters cubed of hydrochloric acid, and we added 5 centimeters cubed of sodium hydroxide over and over and over, recording the temperature change. If you remember from the results that the reaction increased in temperature to a certain point where neutralization happened, and then began to decrease in temperature. If the reaction is exothermic, energy will be released and the temperature of the solution will increase. The more energy is released, the bigger the increase in temperature will be. If the reaction is endothermic, energy will be absorbed and the temperature of the solution will decrease. The more energy that is absorbed, the bigger the decrease in temperature will be. You can illustrate the energy changes that happen during a reaction using reaction profiles. You need to be able to interpret reaction profiles, so these few slides are well worth a bit of concentration. A reaction profile or energy level diagram is a graph that shows how the energy in a reaction changes as the reaction progresses. The graph starts at the energy level of the reactants and finishes at the energy level of the products. These 2 points are usually joined by a smooth curve. There are 3 useful pieces of information you can find from a reaction profile. Firstly, the overall energy change of a reaction is the difference between the energy of the reactants and the energy of the products. You can find the overall energy change of a reaction from a reaction profile by looking at the difference in height between the reactants and the products. Secondly, whether the reaction is exothermic or endothermic. Reaction profiles show the relative energies of the reactants and the products, so you can use them to work out whether a reaction is exothermic or endothermic. In an exothermic reaction, the reactants have more energy than the products because energy is released during the reaction. This means the reaction profile will start high and finish lower than where it started. In an endothermic reaction, the products have more energy than the reactants because energy is taken in during the reaction. This means the reaction profile will start low and finish higher than where it started. The third thing you can look at is the activation energy. Reaction profiles don't normally go straight from the reactants to the products. The graph will curve upwards before it starts to go down again. This is because some energy usually has to be put in to break the bonds in the reactants and get the reaction started. The activation energy is the minimum amount of energy the reactant particles need when they collide with each other in order to react. The greater the activation energy, the more energy that is needed to start the reaction. This has to be supplied, for example, by heating the reaction mixture. You can find the activation energy of a reaction from its reaction profile by looking at the difference between where the curve starts and the highest point on the curve. You need to be able to draw reaction profiles as well as interpret them, so make sure you know how they're set up and how the axes are labelled. That's all for this topic. Everything else is higher tier, so I might make a separate video for that when Year 11 are planning on higher tier entries. But for now, go back to Google Classroom and answer any question that was attached to this video.